Okay, let's see. Let me put this to the side just slightly so I can see. Okay, let's see. But how do I know there's a maximum possible velocity limit? Okay, now I'm going to my notes. Cover that.
Okay.
Did it go away?
All right, go back to the first slide if you could.
Okay, here we go.
Uh-oh.
Okay. Can you still see? The slides went away?
The slides went away.
Okay, let me try again.
We got your email list.
Dang. Can you read the email? Because I could just go over it through email.
Well, I'd like to start off at the beginning. I'd like to start off at the beginning. Go back to your slide, your first slide.
If I can get there. I can't seem to get there. Ah.
Okay, why? I think this is an interesting issue. And the reason I think it's an interesting issue is I think that if there are these different interpretations of special relativity, and what happens is that if you start talking about what is the meaning of time dilation, and you suggest that there's a contradiction in the predictions of time dilation, they say, well, it's not actually a real thing. It's only apparent to the observer in the opposite frame.
Yeah.
Okay. And it just strikes me that if you're going to argue that the effects of special relativity are only apparent to the observer in the opposite frame, they're not actually occurring in the frame that's moving. How could there be a velocity limit in the frame, in that frame? So if the velocity limit wouldn't actually be a limit, it would just only be an apparent limit. Does that make sense?
Yeah. I try. It showed the. Can you see the slides?
Right. So then the question is,
yeah.
What interpretation of special relativity are they talking about? And it looks to me like if you're saying there's a velocity limit, that means that you're using an interpretation of special relativity that implies the effects are real in the moving frame.
Well, I actually get to all of this.
All right. Well, let's go then.
Can you see the slides though, or should I just start reading?
Well, go right ahead with your presentation.
Can you see the slides? Can you see?
Yep, we're going.
I didn't know you could. You can see them. Okay.
Where are we going?
Yo, man, what's up?
Hi, guys.
All right. Welcome, Rick. Let's go.
Okay. I won't be able to see. So here goes. Can you see me? Can you hear me?
Yep.
Can you hear me?
Speak up a little.
You've gone back to your email from the slide.
Well, I'm going to read my presentation. I have the slides are just quick points that I make.
All right.
Here goes the presentation then. My view of the two postulates and how they relate to the Lorentz transformations. I'll start out with my view of the two postulates of special relativity and how they apply to the theory. I'd say I accept the first postulate, which is defined as Galileo's original principle of relativity. The second, which is the most often defined as the invariance of the velocity of light. Okay, this is obvious, but I'm just stating that I accept the first one completely, though I'm skeptical of the second one. There's alleged proof that I'll maintain a degree of skepticism. I'll speak more of my skepticism regarding this later on. The principle of relativity would seem to apply even when there is electromagnetism present. The Lorentz transformations and Einstein's adaptation to it were created to account for the invariance of C. It seems that each of these two similar theories suggests a maximum possible velocity. According to ChatGPT, this was at least implied with the Lorentz transformation, though Einstein made it more of an established idea. However, the idea of the maximum possible velocity limit substitute. My first thought is the question: if something can't travel as fast or faster than the velocity of light, what is that velocity relative to? Of course, for the velocity of an object to exist, it seems to require a direct reference, such as another object or frame with which to track its relative motions. A velocity without a reference couldn't make sense at all. Of course, many experiments have been performed in the lab frame of Earth. However, the Earth spins, orbits the sun, and travels throughout the galaxy, and which exists throughout the astronomically vast and possibly infinite universe. This question would seem to especially apply if the universe expands. It would seem that galaxies would rush away relative to each other at way over the velocity of light. I've heard it said that there isn't any limit to how fast the universe could expand. However, if the maximum velocity limit doesn't apply to objects when they exist very far away, what causes this discrepancy? Is there a minimum distance to which this theory cancels out? Or does this anomaly gradually take effect the further object's relative distance goes away? How to possibly determine this? Okay, on the acceptance of the idea of relativistic mass. It is said that within controlled experiments, scientists have accelerated charged particles to almost reach the velocity of light. Yet, however much they've tried, they couldn't get the particles to reach or exceed c. It is said that the reason why they can't is relativistic mass. The original idea of a relativistic mass was that the size of an object increases when it reaches a velocity that approaches c. However, it seems the idea that mass literally increases isn't even accepted anymore. The theory was somewhat adapted, though, with a more recent view is that relativistic mass doesn't actually grow, that instead its energy increases to the point to where objects could almost reach the velocity of light, couldn't accelerate further, since it would seem impossible to expend that much more energy to accomplish this. Okay, this is an objective look at Galileo's principle of relativity. I've often tried to take an objective view at this scenario.
Jerry.
Yeah.
Why are you calling this Galileo's principle of relativity?
Well, I could go into great detail, but I don't know how to.
Why is it not Einstein's principle of relativity?
Oh, Einstein borrowed it from Galileo.
Okay. So your view is
it isn't always what is used as the first postulate, but oftentimes it is.
Okay, now, of course, yesterday Roger gave a presentation where he said that this is kind of ambiguous. This principle of relativity is ambiguous. And it seems to me this is kind of an issue. You know, what is it, Galileo's principle or is it Einstein's principle?
Galileo originated it.
It's
unclear that Einstein precisely accepted it at first with his 1905 paper, that's for sure. However, though, eventually books started to say that it was they would even cite Galileo as the principle of relativity for the first postulate. I'm sure.
Well, Galileo is applying it to mechanics, to ordinary kinematics and so on. It looked as if there might be some strange things with regard to electromagnetism and optics by extension. So Einstein is endeavoring to apply Galileo's principle to electromagnetic theory and optics, which is following on from Lorentz, I suppose, and people like that.
All right. Now, before we go further, I sort of interpreted Galileo's principle as being that if you're in a ship, you can't tell whether you're moving or not from instruments inside the ship. You can't look outside of the ship, right?
You bounce a ball or walk around just as if you were on the stationary ground.
Provided you're at constant velocity.
At constant velocity. Couldn't distinguish them.
Right. But I don't. So that, to me, that Galileo's relativity means that an instrument that's within the frame, you can't tell whether you're moving or not using instruments within the frame. But if you can look out the porthole of the ship, you can see that you're moving or not.
Yeah. Well, I mean, if you use very precise technical instrumentation, you might detect certain variations that just typical observations you wouldn't necessarily observe just in a casual way. It probably extends way more than casual, though, but you know what I mean.
All right, let's go continue on. I just wanted to understand what you meant by Galileo's principle.
All right, thanks. All right, here we go. I've often tried to take an objective look at this scenario, which involves Galileo's principle of relativity and Newton's explanation of inertia. I'll speak of the Lorentz transformations later on this paper. At this time, I'll review this objective approach. Why would an object that already travels very fast require more and more energy to accelerate to reach the velocity of light? Once an object reaches a given velocity and stops acceleration, starts to coast, it travels at a constant velocity, which is the same inertial state as a stationary object. So it would seem that the energy required to accelerate to reach the last mile per second to the velocity of light should seem the same degree of energy that is required to accelerate a stationary object to reach a simple 1 mile per second. So there doesn't seem any reason why energy would have to build up to where you need more and more energy to accelerate further. Okay, what if our objects and reference other objects and reference frames exist? According to experiments, physicists have accelerated particles. They haven't had success reaching them to the velocity of light. So if a given particle travels almost the velocity of light in an accelerator, what if other particles were accelerated into the opposite direction at a similar velocity? It would seem that the particles would travel well over c relative to each other. So is there a special effect that the Earth has on objects? We recently had a similar discussion regarding the Heifel-Keating experiment and how to determine which frame experiences slower time. Of course, the Earth provides the stabilizing groundwork through its gravity that creates what is often considered an inertial frame, or at least a lab frame, which is effective with experimentation to a high degree. However, is this stabilizing effect involved with why the Earth's frame is adhered to instead of the particles which travel into the opposite directions? Does the Earth somehow create conditions which singles it out as the main frame of reference to go by? How is this possibly so, since each object travels relative to each other, each of which experiences frames which seem equally valid to consider? I recently read A.G. Kelly's paper, which showed that the Heifel-Keating experiment was fabricated. When I viewed the conditions of the experiment, I made a simple mistake. I misunderstood what was meant by carelessly misreading a certain statement. I thought I'd read that the planes were flown at different altitudes. However, when I reread the paper, I realized they were flown at the same height above Earth. If they had flown one closer to the Earth, it would have been said to have gone slower than the plane which was higher because of time dilation with gravity. Anyway, Heifel and Keating seemed interested to find out if two planes flown in opposite directions would experience different levels of time dilation. So they two planes in order to determine this, if the planes would have different experiences of time. I think they might have thought they would, though I'm unsure what their precise theory regarding this was. Given that they flew two planes in opposite directions was a relevant factor to determine the degree of time dilation, it would seem something more than just gravitational time dilation, which causes a discrepancy of these two planes. They must have thought each plane would experience different conditions of time. If this is somehow the truth, it raises many questions in regards to how the Earth functions as what seems the absolute frame in such experiments. Would the different experiences of time within each plane suggest that the Earth's gravity, or maybe ECI frame, has a definite effect on the degree that each plane's time dilates? The Earth's gravitational effect is said to only cause time to go slower compared to outer space, for instance. However, I haven't heard specifically that the Earth's gravity distinguishes itself as somewhat of an absolute frame where gravity goes slower only for smaller objects that travel around within its environment. It is quite a question to consider why the plane's frame of reference would go slower in time while on the ground stayed the same, or that time went faster looking through the point of view of the plane. When time goes slower on one frame, it has to go faster in the other. What causes this difference? What determines which clock goes slower and which goes faster? Okay, this is on the concept of mutual time dilation. There is a certain answer to the question that is often just suggested of what I was just speaking about. First, let's consider mutual time dilation. There would always exist discrepancies in the flights caused by accelerations when the planes land and meet up to compare previously synchronized clocks. However, mutual time dilation exists within relative motions of objects. The the concept of mutual time dilation is when each frame of reference observes only the other frame's time going slower and the length contracting, as you mentioned earlier. Okay, this is demonstrated well by the example of two spacecrafts in outer space which travel relative to each other. They're clearly at the same status in regards to their mass and much smaller gravity fields, at least compared to the Earth's. So how to know which one is actually in motion, and if each is, how fast? They're simply in motion relative to each other, as the principle of relativity suggests. If an observer in one spacecraft wanted to perform measurements on their relative velocity, it could establish itself within a preferred frame, which, for all intents and purposes, is considered stationary. It is thought that mutual time dilation is only interrupted by accelerations, which prevent those same ongoing relative time conditions going further to where a new relative time difference is established. If one or each object is affected by an external source, it begins to experience a different inertial frame. So each, I guess, spaceship instead of object. Okay. So since gravity is equivalent to acceleration, time is also, since gravity is equivalent to acceleration, time is said to go slightly slower in that frame, though the difference would be highly measurable. If this is the sole factor for why there is a time discrepancy between the two clocks that travel fast relative to each other, why was it necessary to fly the planes at such a distance around the world several times? Throughout almost all of the flight, even according to special relativity, the time dilation of the planes and the Earth were mutual. So they could have achieved the same result if they had one quick flight. If the only reason why mutual time dilation doesn't prevail is because of accelerations. Okay. Why you couldn't get anywhere near the velocity of light? Actually, there's something further to take note of. Whenever a given object travels fast relative to a light wave, however fast it goes in whichever direction, the velocity of its light always measures at the same 186,282 miles per second. So if an observer wanted to accelerate to reach and exceed the velocity of light, it seems it could never gain any ground, that regardless of how fast you might travel, you're essentially always stuck with measuring the velocity of light as 186,282 miles per second. However fast an observer might go, it's as if he is always stationary relative to the light wave he travels with. It works this way when an object or observer stops its acceleration and starts to coast, where This is also said to even work when objects accelerate. The velocity of a light wave would continue to register as c. Okay, this is just a quick ponderance over the Lorentz transformations. Okay, I've often pondered why an electromagnetic wave is measured at the complete value of light, regardless of the motions of the observer and source. Is it possible that the invariance of the velocity of light is maybe just a misunderstood and currently unexplained occurrence? What if for some unknown reason light just happens to propagate and register that way when it is measured? Of course, the Lorentz transformations and special relativity were designed to logically account for the invariance of C. I mean, I wouldn't say necessarily logically for special relativity, but okay. However, to know for sure that either one of these theories is accurate, accurately describes what's going on? What if they were just speculation and a hypothesis which gained attention and wide acceptance, since there didn't seem any other way to explain the invariance of C? Or maybe I'm just unaware of certain knowledge which could convince me. Okay, why Einstein might have arrived at the maximum velocity limit. If an observer were to travel as fast or faster than the velocity of light in the direction of a light wave, the velocity of light couldn't possibly measure at 186,282 miles per second, given that the observer would meet up with or outrun the light wave. Similarly, if an observer travels toward the light C, it doesn't seem it can measure the standard value of C. Of course, these scenarios involve the relative motions of physical objects, the observer and the light source. To preserve this conceptual conclusion, Einstein applied these same conditions to all physical objects, even when one of them isn't the light source, and even if light isn't present at all. Other than the mathematical descriptions which were meant to account for constant light velocity, there doesn't seem any reason why a given object could travel faster than the velocity of light. Okay, what if you could reach or exceed the velocity of light? There's also the question of how light would look if you could go as fast or faster than a light wave. It is understood theoretically that if you travel faster than c in the opposite direction of a light source, which just begins to propagate, you'd outrun the wave. However, what if you could go faster than the light wave that propagates continuously? Would you enter into the realm of light, which has just previously surpassed you? Would you see the previous light in reverse, where it's going directly towards you, instead of going with the grain, where you travel with the direction of the light wave? Once you reach that point to where you reach the velocity of a light wave and travel with it at the value of c, is the light in a stationary position? How would that look? This light couldn't possibly measure at the standard value of c, so you also couldn't measure. Okay, better than that. Okay, actually, Einstein had taken some of these thoughts into account and didn't have an answer for them. So he conveniently concluded that objects can't travel faster than c. At least that's my speculation. That's all.
Does that mean you're done now?
I didn't even go through the slides. Are the slides up? Should I take them down? Should I go through the slides?
Why don't we wait until the next thing? We got 5 minutes to go.
All
You
right.
went over that pretty fast.
Yeah.
I guess the issue might be why is this a problem? Does anybody have any comments on why this is does this seem relevant as a discussion to you, or is it irrelevant discussion, or I'm not really sure. Do you have any comments on this, Vladimir?
And I'm not expert in this business, guys. You are all experts. I am, trying to understand through discussions what are the issues are. That's why,
That's
for
what we're
me,
trying.
I told you already, for me, it's only training of mathematics and logics. That's it, simple like this. There is no correlation to the physics at all. I told you many times. That's why
Okay.
I'm very happy to hear you. Thank you so much for your presentation. It was good. Thank you. But I'm looking for the discussion right now of each point of your presentation. Then at last I will understand what are the issues of this special relativity. Because we don't need it for physics, I mean. It's only very good training for our brains.
Well, that's okay. That's one view.
Well, I'm interested in, I suppose there seems to be a basic contradiction which Jerry is talking about, between a system where it's this light ray is going at a particular speed, and irrespective of the observer's speed relative to it, it still remains at this value, which is a contradiction in terms. I mean, the mainstream doesn't object to, say, the Sagnac experiment. We know in principle that there's a difference in the time, in regard to which way it's going around the circulating table. Now, if you view it from the moving observer on the table, well, then the speed of light is varying. It's c plus or minus v. But of course, they can't say that. So what they say is, oh, well, from the point of view of the person in the laboratory, in one case, the distance is closing in because the observer's moving towards the source, and in another case he's moving away from it, so the distance is getting greater. So they've no problem in looking at that. But if you apply the same logic to straight line motion, well, if you have a light ray which is moving in a particular direction and you're moving with it, well, then the distance between you and the emanation of the radiation is closing in. So the distance should be less. And similarly, if you're moving away, the distance should be greater. So how can the speed be the same? Now, to me, actually, just thinking about it in later years, that is such a logical fallacy that it's basically almost a contradiction in terms, and would throw the greatest doubt on this whole business.
That's an interesting review. We got like a minute. I think that's the issue, Ian. The issue is that what we're talking about is in science, we have this fundamental theory. Special relativity is viewed as like a fundamental theory. And we have this fundamental theory that's like a contradiction. And so, how can you talk about cosmology or anything like that if your theory that you're using to describe the universe or understand the universe is the fundamental theory behind it is completely flawed and is got logical contradictions in it? How you know, aren't we just wasting our time if we're believing in general relativity and when general relativity is based on a faulty foundation? That's kind of my point about what the issue is here.
I would say, yeah, it's a waste of time.
Yeah,
You're absolutely right. You're absolutely right.
But if we could convince people that these are illogicalities, you know, they're sort of like they run in the face of all logic. Then of course there are questions. But what they say is, oh no, it's just you have to give up your preconceived ideas of common sense. They're not illogical. They say, the main people.
All right, we're going to get cut off here pretty soon. All right, so I guess we can concentrate on this a little bit. And I think the issue was that Smoot was sort of, the quote that Roger put up there was that Smoot was sort of asking people to take a different view about special relativity and understanding it in a kind of a different way. And to me, the genesis of why he was doing that seemed to me to be that he didn't really see that what special relativity was saying was really a good foundation for cosmology and the universe. And so I think that's what his motivation was, you know, that there needs to be a change. But immediately Roger then puts up what AI had to say, which was contradictory of Smoot. So you know, it's like, yeah, maybe there's a realization on the part of some of these really smart people that there's a problem, but they don't know really what to do about it or how to fix it. That's kind of my take on the situation.
Maybe. I think you're 100% right there.
Well, I would say, like, considering the possible like, if relativity is mistaken, for instance, it raises valid. I mean, it's dealing with valid points to consider. It's dealing with real questions. I mean, they may be theoretical, though that they seem to apply. I mean, you know what I mean?
Yes. Now, my question is, and this seems to be the crux of the issue in my view, if you adhere to the Galilean principle of relativity, which you do, I'm not, and the issue came up yesterday, you know, he didn't talk about Galilean relativity, as I recall, and I don't think that really got highlighted. I think in my mind, the Galilean principle of relativity is not the same thing as the Einstein principle of relativity.
Possibly so.
And not the same thing as, and I think what Nick Percival was trying to say is that's not the same thing as the Lorentz's principle of relativity or Poincare's principle of relativity. I did write a paper on this many years ago. It's at the GSJ, where I ask about what happened to the principle of relativity. And it turns out that if you start looking into it, you find out there are different opinions about what the principle of relativity means, whether it's the Galilean principle, which I interpret to mean you instruments inside the ship can't determine whether the ship is moving or not. I view that. Then Poincare has a different version, and Lorentz kind of had a different principle, and then Einstein comes along. So are they all the same principle? Do they all mean the same thing, or are they different principles that have subtle differences that should be understood differently? And okay, I'll let you talk.
Well, I, I would say that the only principle, the only first postulate that I accept as truthful is Galileo's original principle of relativity. I'm sure there are many other variants, which I mean, if I could read them in particular, if they were consistent with that, I might agree. But if they contradict that in any way, I wouldn't agree.
Okay, but what is Galileo's principle? Is it what I say that you?
Well, I don't think they had. I don't think they had precise instrumentation at that point in history. I mean, they were just dealing with just sort of just observations. I mean, it seems that like an inertial object, an object that doesn't accelerate, it stands like there's stationary relative to it, actual state that it exists without.
And Newton's first law, building on, and something that's stationary or an object which is moving at constant velocity. There's no reason why the one moving at constant velocity should ever change its state of motion unless there's an external force impressed upon it. It'll go on forever and ever. And that is true, but it is an idealization, because in the real world we have, say, friction. And even if you don't have this heavy friction with the ground, say, you have air. So if you had a very, very delicate piece of equipment, you could actually find that you're moving relative to the air, and therefore the idealization of the first law wouldn't apply. Now, in the same way, well, at least I would argue, you have a medium, you have an ether, if you like, a local ether, let's say, and that would give you a means of reference for an electromagnetic radiation passing through it.
Okay. All right, here's my proposition. This is why I asked Jerry to talk about this. According to the Galilean principle of relativity, if I have a particle accelerator, okay, and I'm moving at, let's say, 0.999% of the speed of light with my accelerator, and I try to make my accelerator work, my accelerator is not going to work because it can't accelerate particles, okay, because I'm almost at the speed of light, right?
Well, you said Galilean, Harry. No, Galilean relativity wouldn't rule out anything connected with the speed.
What I'm saying is that if you believe in Galilean relativity, that's contradicted by special relativity that says that I can't accelerate particles any faster.
Well, the invariance of C brings in a what presents a question, because it's unclear why would light always travel at the same value regardless of the relative motions. I mean, I think one reason why Einstein had the first two postulates, he must have realized they seemed sort of contradictory or incompatible, so he wanted to unite them. I mean, I
think they are contradictory. That's the problem.
Well, I mean, it wasn't immediately clear. I don't see how they're contradictory though. Okay, if the velocity of light is invariant, it doesn't necessarily imply that the Galilean relativity is mistaken somehow, though. I mean,
I don't know why you are always talking about are wondering about the invariance of the speed of light. Don't we know for a fact that the light speed depends upon the medium? We have refraction, where light is slowed down as it passes through, say, glass, from air to glass, and is different in air than it is in perfect vacuum. So that the last thing that we have as far as the velocity of light is any idea that it is invariant.
Well, ideally, they call it a vacuum where it travels at the complete value. However, though, of course, light and water and such, I mean, like glass and water, for instance, could slow it down. But still, though, I mean, like, okay, like say you're measuring it through water, like what like 3/4 I've heard is the value of C that it is somewhere around there. So like if you're underwater, it would always register at that 3/4 of C. So why is that? I mean, you know what I mean?
Well, it is true that we use the term in variance of the speed of light, or it's used frequently without cognizance of all the different situations. I think Roger raised some of this yesterday as well. However, there's a more fundamental difference, and that is what I would call the non-symmetry between observer motion towards a light source, which say is stationary in a stationary frame, or light source moving relative to a stationary observer. Now, that is never mentioned when people are talking about this. And I'd go so far as to say that the statement of postulate 2 on page 2 of Einstein's 1905 paper, where he says we can take these as axioms, is actually correct. It says, literally it says this, it says, the speed of light is independent of the speed of the source. Now, that is true, but it's actually redundant. So what? Every speed, every light wave, every wave, the speed of every single wave is independent of the speed of its source. So in other words, if you have a sound wave in air and you have the object which is actually moving, the speed doesn't change. It's actually determined by the still air. Similarly, if you have a pond of water and you have a water wave brought into that by a moving object, no, the pond is the frame of reference which there's no. So that it's actually correct what Einstein says. Postulate number 2 is correct, but trivial. It shouldn't have been mentioned. Now, what they've done is they have then introduced, well, he did it later on in the paper, they've introduced a symmetry to say that's also true, independent of the speed of the observer. Now, that is demonstrably incorrect, both experimentally and theoretically.
What is again?
What I've said is the speed of light is constant, independent of the speed of the source.
Yeah.
That is correct. That is actually a correct statement. The speed of light is constant, independent of the speed of the observer, relative towards or away from the source. That is incorrect.
Oh, really?
Yes, incorrect. And it can be demonstrated experimentally, and it can be demonstrated theoretically.
Well,
one demonstration of it, by the way, the other week, which is an old one, 17th century one.
That's reminiscent of how Einstein viewed the magnet and wire creating the current. Like if the magnet's in motion, I forget which is which, but if the magnet's in motion, the current creates a wire, and there's an electric field within the vicinity of the magnet. However, though, if it goes the opposite way, the electric field within the vicinity of the magnet isn't there. So I don't know if that applies at all.
Yeah, well, that's true. And again, I mean, my own view on this may not be accepted by everybody, but I accept the principle of relativity, or Galilean relativity, I prefer to call it, with regard to electromagnetic induction. And that's how I've endeavored to explain the Faraday paradoxes. And I suppose Einstein had that in his mind when he wrote the first sentence of the paper. Yeah, that's quite correct.
Ian, I'm trying to understand what would seem the difference between, if an electromagnetic source, like if it's being detected, if the observer is in motion or if the light source is in motion. I mean, if one or the other, you said that one certain way, like if the observer moves away, that C isn't invariant. But if that's true, I mean, what are the relative motions of the light source and observer according to Galilean relativity? Why wouldn't that apply?
Well, Galileo doesn't talk about.
Oh yeah.
That I mean, he wasn't absolutely sure whether the speed of light was instantaneous or not. He thought it probably was finite. He claimed to do an experiment with an assistant where they stood on hills, maybe a mile or so apart, and one put took the shutter away from a lantern, and then the other recorded the time, and he got practically zero time. So he said if light has a non-instantaneous speed, it's very, very great. That's what he said. So he didn't talk about that.
Yeah.
But I think a better analogy is to look at wave motion rather than motion of a cart or a rocket or something like that, a mechanical thing. If you look at some water, some still water, and you have a disturbance in that water, and you are stationary in the water, in the frame of the stationary water. Well, you'll find that this moves towards you at a certain speed, which is determined by the properties of the water, basically. Now, if that disturbance is actually moving relative to the water, and you measure the speed of the wave that actually resulted in the water from that object, it remains the same. That is true. However, if you were a swimmer and you are swimming towards that wave, well, then the speed increases because you add to it your speed of motion. Now, as I say, the mainstream people, when they try to explain things like Sagnac, they say, oh, well, that doesn't mean the speed changes. You're actually reducing the distance between you and the wave. Yeah, well, that's from your point of view. But from the point of view of somebody actually in the unit itself, the speed is actually changing. It's just two different ways of looking at the same thing.
Well, would that suggest though that I've heard that sound waves that they're constant just as well as light waves? Though I'm skeptical of that. I mean, it seems that for instance, if there's just stationary air and there's a sound source, the wave travels. I mean, relative to say, okay, like for instance, if there's a light source and the observer travels away, or you had said that there's a difference there, but if the light travels away, for instance, for one observer, sound would get to them slower if they traveled away, which according to light, it would arrive at the accepted value of C.
But it doesn't. You're just repeating, with respect, Jerry, what you're reading, that it arrives at the value of C. It doesn't.
Well, I didn't read that anymore. I just thought of it.
Yeah, well, that's what they say. It's almost like a dogma, and they're not.
So it is constant though.
They're not making the distinction
sound waves are constant
now about whether the source is moving or whether the object is moving. So, for example, if you're standing in still air, and you have a police car coming towards you with the siren, moving. Now, if you work out the speed of that sound wave getting to your ear, it's constant. But what actually happens is the frequency changes. The frequency would get.
Oh, I would agree there.
And the wavelength gets longer. Now, and conversely. Okay, but
if it does, like as fast as it travels.
If the police car is stationary and you're moving towards it, well, what happens is the speed of that sound increases by the speed of the sound plus your speed towards it. Yeah. And what actually happens is the frequency also increases, but the wavelength remains constant.
Yeah, I see what you're saying. That's good.
Yeah, good. Yeah. So it's analogous. That's my argument, anyway.
Okay, I think we got off topic. And this is kind of, I think, is what the issue is. If you start talking about the principle of relativity, you wind up talking about the invariance of light. And if you talk about the invariance of light, you wind up talking about the principle of relativity. And I think what happens is you kind of go in this circle. And if you try to pin down a defender of relativity, they put you into this circle of, well, the explanation of this is this thing over here. So if you try to understand what's going on with the principle of relativity, you get sucked into the velocity of light is invariant. And if you try to understand that, you get sucked into the principle of relativity, and you can't really decide which one is wrong. You see what I'm driving at?
Yeah, well, yes. I'd say they involve each other to a degree.
I don't like using the term relativity to mean Einsteinian relativity. you know, and you were right, Jerry, I think, to bring in this concept of Galilean relativity, because we need to discuss it. It's the basic fundamental principle on which, say, Newton's dynamics is based. But when we say a relativist is such and such, you know, that doesn't indicate whether he's an Einsteinian relativist or not. We really should qualify it. For my part, I object
Well, they're
to.
not clear about it.
Who's not clear?
They're not clear about it. The mainstream, they've basically essentially incorporated all this stuff into the textbooks. They've said, well, Einstein was responsible for it. He said he's going to unify mechanics and electrodynamics into the same system. Okay. And then essentially, I've got two postulates that I'm going to do. And they seem like they're contradictory, but they're really not. But they really are contradictory. That's the problem.
Yeah, I'm more concerned with the imprecision of calling relativity Einsteinian relativity and misquoting the second postulate, or at least not being clear as to whether you're talking about the source or the observer or both. I'm more worried about that than what Roger was going in about, these small details about, you know, translation and this, that, and the other, and whether they're not referring to, you know, the transmission through refractive media and so on. He's right in these, but you could start, you know, splitting hairs ad infinitum on these. There are more fundamental principles, and that's being unclear about what relativity means and what you're talking about.
Ian, what are the details of the experiment that proves that when an observer travels away from an electromagnetic source that it isn't invariant? Is there a name for it? Look it up, or could you?
Well, I keep on, yeah, Jerry. You've put me in the hot seat, and that's fine. That's very fair. There are a number of, but I keep on going back to the first experiment over long distances, which is Romer's experiment found that when the Earth was moving away from the light source, which was coming from the moon Io, that the period relative to when it was static, you know, it wasn't moving either way, actually increased. And it increased by, I gave actually figures which weren't quite right a few weeks ago. I've looked it up in detail now. It seems to be very, very small. It's about 15 seconds. So in other words, the light from Io was coming towards the Earth. Now, when the Earth was moving away, it took an extra 15 seconds to get there. So, there was 15 seconds less when the Earth was moving towards Io. Very, very small amount. But that's one proof that you know that the speed of light does change. And if you look at it from the point of view of mere distances, of course, because the Earth is moving away, and even though the light is very much faster and is going to overtake it, it still has to, you know, go this extra distance, which is accounted for by this extra 15 seconds. Now, I'm sure there are more modern experiments done on this. But people are not looking for that. It's a dog.
I agree with you, Ian. The issue, though, that we're talking about, that we're starting off with, is the Galilean principle of relativity. Why are we talking about the speed of light when we were supposed to be talking about the principle of relativity?
As you mentioned earlier, they're inherently involved. I mean, they don't have to be. You can picture a scenario where there isn't light present at all. However, though, you know, it's relevant to consider, well, when you introduce light or electromagnetism, what happens, you know?
And you see, I mean, maybe I'm harking back to something which is a little tangential now, but I've said it many times. I mean, if you introduce the Lorentz transformations into the Maxwell equations, which lead to the wave equation, you know, you just get the curl of the E and the curl of the H and so on, you'll get a constant speed. You know, you'll still get the second partial differential with respect to distance is 1 over c squared times the differential with respect to time, and it's constant. However, if you say, well, what happens if I substitute c plus or minus v into that equation rather than c squared? So, the second partial differential of the distance is equal to 1 over c plus or minus v squared times that. You work that back. I might give a talk on this at some stage, by the way. It's quite simple. You work that back. What will you get? You will get a total differential, in the Maxwell equations or in the wave equations, a total convective differential, which is what is used in fluid mechanics. So why shouldn't we use it when we're talking about the motion of electromagnetic radiation in the medium, let's say? We won't even use the term either.
Well, because the mainstream doesn't want to do physics that way.
That's right. That's right.
So the issue is we're talking about the speed of light when we should be asking about Galilean relativity. Is Einstein talking about Galilean relativity, or is he talking about something different that he's redefined? And I think my own view is that Galilean relativity can't be consistent with Einstein's conclusion that there's a limit to velocity limit to how fast you can make particles go. I don't think that those two are consistent. That's my point. And that's what Jerry is asking.
I think he might have partly arrived at the maximum velocity limit because of the invariance of c to account for, because if you travel faster than a light wave, you couldn't possibly clock it at its standard value. And I don't know for sure, but I've considered if you travel towards it at c, it seems that you get, so I wouldn't say a null figure, but I'm not quite sure. But anyway, if you were to travel as faster, then there's a question of how would light look at stationary and such. But I think it was the invariance of c that led to the idea of the maximum possible.
Well, that's right, Jerry. But another example is the one which the mainstream give in the counter way that they should give it. So in other words, it's GPS. It's our experimental view that if we send out a piece of radiation going in particular, forget about Haffel and Keating for a moment. That's probably fabricated. But anyway, if you send out a radiation from an emitter, and then the Earth is actually spinning towards that radiation, well, then we know by experience that the speed becomes reduced by that amount. And conversely, if it's going the other way, we know that the speed is increased by that amount. You say, is there any experimental evidence? Well, the GPS, I'm going to turn on its face what the mainstream say. The GPS wouldn't work if the speed of light were constant. It has to take that into account.
Well, be careful here, Ian.
Yeah.
I understand what you're saying. I believe that the speed of light is constant, but it's only constant in the preferred frame, which is the word that people really hate to hear. Could say it's the absolute frame, could say it's the stationary frame, could say it's the preferred frame, but there's only one frame in which it's constant. And you find out which frame that is by, is the speed of light isotropic in this frame? And GPS says, yes, it is. It's constant in that one frame. But if you're moving relative to that frame, you don't get the speed of light's constant anymore.
Yeah. Well, that's the ECI frame, because what we found experimentally, and we could try to explain this. I've tried to explain it, maybe not totally successfully, but we know that the Earth in its revolution around the sun, its annual revolution, does not add or subtract to the light speed. That's right, because it's approximately inertial, or if you like, there's an ether drag.
Well, the bottom line is that the motion of the Earth around the sun would show up in the GPS because it would add to or subtract from the velocity that you would calculate in your range calculation. So you would get an error depending upon what side of the Earth the satellite or the Earth station is, you get an error because of the Earth moving around the sun, and that error doesn't show up.
That's true. That's what I'm saying. But what does show up is the rotation, the diurnal rotation of the
And
Earth.
that's called the Sagnac effect.
That's correct.
So what they do is they compensate for the rotation of the Earth during the time of flight of the signal from the satellite to the Earth station. So when the satellite transmits, the Earth moves from one position to another position, and that's taken into account in the range calculation. And that basically means that you're calculating the range relative to the ECI, not relative to the surface of the Earth.
See, they make sure that it works. You know, you have to hand it to them.
Well,
they get it right. But they go through all mental gymnastics to try to explain it, because that fact in itself, the Sagnac effect, you know, it disproves this principle that Jerry's been asking about or talking about. And actually, I'm not really a fan of GPT, but I put a question into it the other day. I said, does the Sagnac effect contradict special relativity and the constant speed of light? And it went into all mental gymnastics. No, it doesn't. It may appear to, but it doesn't. You know, just rehashing all the sort of stuff that you will see on the internet, but not explaining it properly.
Well, if you look at it from the point of view of one group of people will say, well, this guy Sagnac disproved Einstein's second postulate in 1913. Okay, so they disproved his postulate in 1913. Okay, so they ignored that. So, you know, that's a problem right there. Okay. Okay, so so they accepted a theory that had been disproved by an experiment.
And it's amazing that they try to explain it away. You'll find you can go into the internet and
the argument is that the Sagnac experiment is not an inertial frame. So Einstein said inertial frame. So there's your get out of jail.
Okay, so that's one argument they give. That's very true. But it's strange how there's such a breakdown in the Einsteinian mechanics, whereas Newtonian mechanics works for both. Newtonian mechanics works for non-inertial. If you analyze the Sagnac effect in terms of Newtonian mechanics, you get the right answer. But why don't you for Einsteinian? And then, of course, there's the other argument. If that doesn't convince people that it's really a bit of a cop-out, you have the linear Sagnac effect, which was
Wang.
I've been trying to persuade him, by the way, to give a talk to us. So far, without any success. But not because he doesn't like us or anything. He's happy to keep in contact with us, but I think he's not happy talking about it. But he's done experiments which shows that you get the same effect, and the only reason to have the return on this sort of like fiber optic conveyor, like the track of a tank, is to bring the light back to its source so you can compare it. But the vast majority of the transmission is done in a linear way, and you get the Sagnac effect based on the actual perimeter, not based on the non-inertial part.
Okay, but still, my view is that if you do an experiment and you're in a spaceship and you do an experiment and you find out that your particles can't go faster than you're accelerating your particles in your spaceship, and you find out that they just can't accelerate, then that means that you're moving close to the speed of light. And that's a violation of Galileo's principle, because Galileo says your instrument shouldn't be able to do that. You shouldn't find that happening with your instrument.
Oh, one thing I've heard is that, like in regards to, what's the velocity relative? Like, why can't you go fast? Like that nothing can travel faster than the light relative to anything. For instance, just anything at all if you consider those two frames of reference, it like just in between them only, that there's it gets more complicated with the Lorentz transformations where they say that linearly velocities don't add. That I've heard years ago, where you can get like almost double the velocity of light somehow, but that still doesn't explain why on Earth, if the Lorentz transformations would allow that, why, such as with particles going in the opposite direction within particles acceleration, when there's certain particles traveling almost velocity of light and particles traveling the other way, those particles relative to each other way exceed the velocity of light. However, they say the Lorentz transformations accounts for it somehow. I'm unsure of how. This is something that I heard many years ago.
It's the formula. They say it's the sum of the speeds divide or difference divided by 1 plus v1 v2 over c squared. It's just really an artifice to ensure that c cannot be exceeded.
Well, the issue about C not being exceeded is, in my mind, in what frame can it not be exceeded?
Yeah.
That's the problem, you say. So in the frame of the Earth, and you do a particle experiment and you shoot particles in a straight line and find at some point the particle's velocity relative to the Earth accelerator, there's a limit. Well, why would that a limit apply to another frame of reference is what Jerry is asking. Does that apply to another frame of reference? And the answer doesn't. And relativists say, well, but the laws of relativity apply in the other frame, not in the frame of the rest frame. So the limit should apply in the frame it's moving relative to the Earth frame, but it doesn't, according to the experiments. So the whole thing seems completely contradictory. That's my conclusion. I think Jerry's sort of trying to struggle with it.
Well, yeah. Also, though, as I mentioned earlier in the presentation, there's the question of, I think Ian mentioned in a session how, like galaxies in the whole universe, like if you go far distance apart, they're traveling, even accelerating way faster, like several times faster than the velocity of light. So how is that possible?
Yeah, I'm not even sure what the general accepted view of that is, because if you put in the equations, the Hubble type expansion business, you do get at some stage they accelerate faster than the speed of light if you accept their principles. But they also have another equation which modifies that to make the speed of light c the limiting speed of recession of the galaxies. So I suppose it depends who you actually ask.
Okay. All right. Well, we can talk about that. We're almost running out of time. Do you have any comments? Any other comments? We got about.
There was one quick thing I wanted to say, but
about a minute. 1 minute.
Okay, I'll be very quick. So sorry, my cat is. The excuses they're making about the Wang experiment and so on. If you have some dispersion in light emission, the group velocity is greater than the normal value of c, and the phase velocity is less, say 0.99 or could be c. The group velocity is greater than c. So what do they say? They admit that and they find the experiments, but they say, oh, but it cannot transmit any information. So that's their out in that case.
There seems to always be an excuse. And that seems to be the problem. And so we can't really actually get to what's really correct, because there's always these get out of jail cards and exceptions. This doesn't apply to this case here. And so we can't really get to we're not really getting to what really is the physical correct interpretation or understanding. We can't, because we're totally confused. In the case of JWST and the telescope, what happens is that the as they look farther and farther out, the radiation gets redshifted. Okay, so as so that their argument would be that since the velocity of recession is getting bigger and bigger and bigger, the redshift gets larger. The frequency shifts to a lower frequency, and so what would happen when you get to the ultimate limit, you wouldn't be able to see the object because it would be redshifted to zero frequency or below. That makes sense. You really can't. The object gets shifted and you can't really see it anymore.
Oh, like it's in the infrared or something like that.
Yeah, the thing that was confusing, that's kind of the obscure aspect of JWST that they don't really tell you that much about, that puzzled me for a long time, because I didn't really know that much about what they were doing. But it's an infrared detector. It detects in the infrared. It doesn't, but when you see the pictures, they convert the infrared light to visible light. So you're looking at these pictures and it shows these galaxies as being red, but they're not red. That's just an artificial, they just translated the frequency of light to make it appear red. So yeah, okay. But it's really infrared.
So this is what they sometimes entitle what they call artificial. No, there's another word.
False color is usually the one.
False, that's it. Yeah, false color. Yes.
So, and it's kind of misleading when they show you these pictures of galaxies and then they show you these pictures of all this stuff taken by the JWST, and you think you're looking at a picture, but you're really not. You're looking at an infrared picture. Okay, you're not looking at a visible light picture. You're looking at an infrared picture that they put false colors into it so that to make it a picture that's comprehensible to you as a human being. But it's infrared, it's not visible light. And so what happens is you go further and further out, the light gets shifted lower and lower in frequency. And eventually, when you get to the limit, it should disappear entirely.
What is that limit?
I'm not really sure.
I don't understand that. What is that limit?
Good question. I'm not really sure. When Z becomes infinity, I guess.
Well, it may be when it becomes 100,000 or something, because it's surely human perception. Theoretically, if we were looking at something and it were only reaching us in the infrared, we couldn't perceive it as visible light.
Correct. But the telescope can. That's the whole point.
Well, the way I understand the age of the universe and redshift is that they read the redshift of an object and they determine that it's this distance away and it's moving away at this distance. Now, the observable universe limit is the limit that you're talking about here. They say that since the Big Bang, light propagated at 13 million years ago. There was no light any past 13 million years ago.
Well, you mean billion.
Or sorry, billion, yeah. There's no light past 13 billion years ago, so there's no observable universe to observe. Well, every time they stick a new telescope up, they see things further and further and further and further and further out. And now they're about
the biblical version.
They're about to change. They're about to change the age of the universe up to 26 billion years now, because they can start seeing more further objects, and the observable universe keeps growing every time they stick a new telescope up. The observable universe is only a limitation of our equipment, of our technology. They're going to find that the universe is the extent of the universe is unknowable, and once they understand that, all of this stupidity talk about ages and it's going to go away because again, they're going to keep finding more and more and more
Uh,
as the technology gets better.
Rick, you once showed me a picture of a certain galaxy, I guess, that was clearly connected to a small mini galaxy. Maybe it was connected.
It's connect. It's connect.
And
We're talking about the work of Halton Arp and
yeah,
his work with redshift.
well, that
And
suggests that
I can't.
redshift is an alternate theory.
It's an NGC galaxy. I can't remember what galaxy it is, but there's a physical connection, a physical plasma connection, which is observable with our instruments, and it's physically connected to this galaxy, which is less redshifted than the quasar. But they say the quasar, because of its redshift, is billions of light years away from that galaxy. Well, no, it's obviously connected. You can see the obvious connection with your telescope. And there are other redshifted objects within the connection, other smaller quasars within that connection that are redshifted as well. And they say that they're behind that galaxy, but they're not. They're inside that physical plasma connection between the two objects. One is a galaxy, a full-blown galaxy, and the other one is a quasar.
Yeah.
Halton Arp says that quasars are birthed out of galaxies, and they grow into full-fledged galaxies eventually. And as they turn into a full-fledged galaxy, their redshift quantizes, it changes. Their redshift drops lower and lower and lower as they age, and they get bigger and bigger and bigger, and more matter is created within their cores.
Is it the size that causes a redshift, or just I don't understand how the age would affect cause a redshift?
Well, it's just how quasars grow from smaller objects into a larger object. It's just I can't explain it. I think it's due to the fact that the plasmoid in the center of the quasar is creating matter.
Well, one point that is I've not heard mentioned is the redshift may not indicate distance, as everyone seems to believe. It could just
That's
be
what Halton
that
Arp says.
light emitted from various objects, faraway objects, has to pass through a lot of matter
Tired light.
in order to reach our telescope.
Yeah, it's called tired light.
Yeah, that's my view as well.
Yeah, exactly. Thank you.
What would cause the blue shift? Vladimir has stated that there's some 8,000 something blue shifted galaxies. So what's
for reminding this blue shift, even our neighbor galaxy is moving to us. What about your tight light? I don't understand, guys. Jerry, thank you so much for recording this.
Well, I'm provisionally willing to accept that these blue shifted galaxies are actually moving towards us, that there's some Doppler effect there. But the whole panoply of the universe, which gives the redshift, and it seems that the further away, the greater the redshift. I think both on theoretical and experimental bases, I take those to be non-Doppler. I take them to be a tired light system. Yes.
I'm sticking with Halton Arp and saying it's a factor of age of an object. Their redshift.
Is it possible that the universe is somewhat static, that it doesn't expand at all?
That's what Halton Arp says. It's a static universe.
Wow. So
that's my view as well.
If that is so, was there a beginning?
Well, I mean, there's no sense in talking. There's no sense in talking about a beginning or an extent, because it's unknowable at our current level of technology.
Well, the Big Bang Theory, the Big Bang
It's
Theory
all speculation, and
speculates.
there's really no sense in
Yeah.
speculating
Well,
how
why
old it
guess?
is or how big it is, because we can't, we don't know.
Yeah.
You can guess all you want, and your guesses are going to be wrong, proven
Why
by
assume there was a
the
beginning?
fact that they're about to change the age of the universe again.
Why have the belief that there was a beginning, though? I mean, it seems that infinity is something to consider, time
Uh,
and space.
It seems that everything has a beginning and everything has an ending from our perspective.
Well, maybe in our day-to-day lives, you know.
Well, that's what I'm saying.
Well, that doesn't mean that applies to the universe at large.
Well, I understand that, and
Time and space and such.
I agree with that.
They may indeed modify the so-called age of the universe in light of the
New
distant
observations,
objects. However, I think they will probably still try to explain it away in terms of what they call expansion, an early expansion.
obviously.
Hmm.
And it's going to, 26 billion years, and then 56 billion years, and then 120 billion years. The the better and better and better our telescopes get, the more and further we're going to be able to see. It's this observable universe is only limited by our technology. And I'll say it again. The age of the universe and its extent cannot be known at the moment. Once
Well,
we
the
once we
whole
get to
Eternal.
once we get to the point where we can move from here to the edge of our observable universe and set up a telescope, we're going to be able to see even more further and further out there too. So,
yeah.
I mean, it's it's a non sequitur question for me. I don't even like enjoy talking about it.
That's
It's
cool.
a waste of time as far as I'm
I
concerned.
enjoy it, and I think it's a
But
relevant topic, but that's my
but
opinion.
but Halton Arp states that the universe is static, and that the redshift of objects is based on their youth,
Yeah.
and I agree with that.
Well, as far
Every,
as
every
the observable
everything.
universe, as far as
eh,
the observable universe goes, I mean, what we can currently observe is maybe just a speck of dust in a gigantic ocean, or even smaller than that, or even on a vast scale of infinity that we can't even conceive of. Just a thought.
Well, I think my view is that what the scientists are saying about the universe is colored by their foundational physics beliefs, and the foundational belief that they're talking about as far as the universe is concerned is general relativity, and that's based on special relativity. And it looks like special relativity is a contradictory bunch of nonsense. So to
Well,
me, that's a problem.
I would say the first two, the two postulates of special relativity, if specifically defined as Galileo's principle of relativity and the invariance of C, which I'm skeptical of, but there's alleged experiments for, so it's possibly the truth. So both postulates are possibly true. However, the derivations of time dilation and length contraction and relativity of simultaneity is highly doubtful, I would say.
I would say that looking at special relativity and relativity as the starting point is wrong. Cosmology is the mother of all sciences. We get our physics from looking at cosmology.
Right. No, they're doing it backwards. They're looking at
Exactly.
cosmology from the lens of special relativity and general relativity. And
And
what
that's
they
wrong.
see has to be consistent with those two ideas. And so what happens is they look out at galaxies and they see things going on in the centers of galaxies, and they say, aha, those are supermassive black holes because
Or or they
theory
name
says so.
or they name something the Newton's cross, or sorry, the Einstein cross,
Einstein.
or it's stupidity what they're doing. They if again, if they added the electric force, all you have to do is add the electric force into the model that they already have. then that would explain a lot of things. It would explain a lot of actions of the stars. It would explain how stars run. It would explain how galaxies are pinched into, and the motions of the stars on the outside of the galaxy are relative to the ones of the inside of the galaxy, not them turning faster inside and slower on the outside. All these the observed rotation curve of galaxies is explained by this electric force holding everything together. Same with the creations of suns. It pinches and creates a sun, and plasma is in arc mode discharge, and there's no atomic engine within a sun creating all of this heat and light that we see, all of the transmutations of elements as well. All of that's happening on the surface of the sun.
Well, as far as that we shouldn't start out with the ideas raised by special relativity. I mean, if we start with cosmology, where do we like? How do we eventually arrive at special relativity to consider it? Like, what can we learn from cosmology in order to correctly assess what's correct within special relativity, if anything, or the concepts raised, which may differ greatly from Einstein, which they seem to?
Well, we know that plasma bends light. Well, there's an explanation right there. Plasma sheaths around bodies in space will bend light around that body, not gravity, which is
Well,
which is
phenomena
the
is
relativity
experiencing.
stuff.
That phenomena is experiencing, though, the two postulates. I mean, those are included within the
Yeah, but it's explained by a plasma sheath around a body in space. Every body attracts plasma towards its gravitationally, and then that causes a sheath of plasma around it, and the light will bend through that plasma around that object. No need for relativity or special relativity there. That explanation is handed to you right there.
Well, they always seem to apply, though.
What seems to
With any
apply?
physical phenomenon.
What seems to apply?
Galileo's principle of relativity and the invariance of C. Just that there's electromagnetism.
Yeah,
which
but
is
I'm not
plasma.
talking about C in this instance.
Well, you're speaking of specific conditions that are observable, which have validity, I'm sure. Like I agree with much of the electric universe theory. Even you have doubts, of course, but I think there's much of validity that they say that's possibly the truth.
Very small doubts. There's questions that come up, but like any theory, there's questions that come up in any theory, and
Yeah.
it just depends on how many questions come up for this theory or that theory. There's far less questions in the electric universe theory than there are in other theories, the
Okay, I'm
standard
tired
model.
already. Let me ask you the question about the electrical plasma, or I don't know, universe. We have solar corona with X-ray radiation. And the size of this corona about 10 times more than the size of the sun itself. Please answer the question. What is the source of these X-rays from solar corona 10 radius of sun outside of it? Your
The
plasma
accelerate
theory.
the
And
acceleration
temperature
and
of this solar plasma calculated. It's
the
electron volts,
if
12
you
mega electron volts, and all this stuff. How to explain based on your understanding of sun?
we know that the acceleration of electrons, the motion of electrons creates X-rays.
Acceleration 10 times further than diameter of the sun. Are there forces? Because there are no forces. I told you many times, guys. There are no forces. We invented them. But your explanation, why? Only one experiment. That's it. Simple like this. Solar corona, 10 times diameter of sun, and you have X-rays from this area.
Huh.
And that's
Not
it.
only
And
not
end of
not
the story of your plasma.
the solar
I-
well, if you don't let me talk, then
Answer, not talk. Answer.
so ask the question again, because you keep going on and on and on, and you don't like, what's the
Three
question?
times I asked the same question. You don't have an answer. That's why you want to repeat one more time. Okay, I'm ready. You have solar corona, 10 times diameter, more than the diameter of the sun. And
Right.
it radiates X-rays. Please explain me.
Motion of electrons creates X-rays. That's
All
it.
right,
Simple.
I'm going to sort of intervene here. We're sort of running out of time. I think the real issue here is, and kind of goes to my point, and I agree with you, Rick, on this, and you put it pretty clearly. I think that science should be based on looking at the phenomenon and then trying to explain the phenomenon that you observe. They've sort of reversed the procedure since Einstein by imposing a theory on what they observe. And this is in particularly with respect to cosmology. So what they observe is interpreted through the lens of theory.
Yep.
And if that theory is wrong, then their interpretation can't possibly be valid. So why
Right.
are we stuck with an interpretation that's viewed through the lens of a theory that doesn't make sense?
Well, then you have to throw ad hoc on top of ad hoc on top of ad hoc to,
Which is what they're doing. So
yeah.
now the issue becomes, how do you demonstrate? How do you convince people? How do you talk about, well, we can't really believe this special relativity theory anymore. It doesn't make sense. It's full of contradiction. How do we get rid of it? How do we view the universe? How do we view what's going on around us in terms of actual science, which is you observe and you try to explain. You don't observe and then say the theory is this proves our theory is correct. In other words, we see something out there that's like, as Vladimir is pointing out, how do you explain the X-rays in the corona? Well, they don't know, so they don't bother to try to explain it.
Well, I would
Because
suggest
one
that I'm
experimental result, it's enough to stop theory. If you cannot explain one, but
I
thousands of them, how to explain?
I'm not the person to be asking about the X-ray source from the sun. I think Donald Scott would be the person that could answer that question for you. But I would suppose that if all the transmutation of elements is happening in the corona and on the surface of the sun, there's your source of X-rays right there. And gamma rays and beta rays and all the other rays that are electromagnetic in their origin.
Yes,
Right.
you
But
are
the
right.
problem,
Solar corona get even gamma rays with hundreds of mega electron volts, giga electron volts. How to explain it based on your plasma theory?
There's an electrical curve that explains you have to have a certain amount of energy to get past the corona of the sun. I think Harry might be familiar with this curve. It's the relationship between glow discharge, or sorry, dark mode discharges, glow discharges, and arc discharges.
okay, well,
I'm tired.
I think Vladimir is sort of, this isn't really the topic of our conversation today. Maybe we can talk about it in a future thing. I think there's a hole in this, the way they're doing science. I think we agree on that there's a problem here.
Let
Well,
me make
if
some comments about really. I agree absolutely with you. But guys, first of all, comments only. In Maxwell equation, there are no speed of light in vacuum. Forget it. It's an electrodynamic constant measured even before Maxwell. He found that the speed of light close to this electromagnetic constant. It doesn't depend on anything. That's why, guys, when you name your Maxwell equation, don't forget there is no speed of light in vacuum. This is the first point. The second point, do you know about this Cherenkov radiation? Cherenkov radiation, it means that in glass, speed of light 1.5 times less than in vacuum. And you have your particles going with in vacuum with speed more than 0.75 speed of c, and it's going inside of this glass with speed higher than, bigger than speed of light. How to explain movable particles, electrons I mean, inside of the medium faster than speed of light in the medium? Cherenkov radiation, it's well-known experiment.
Where
What
is
we
that
talking
observed?
about? What kind of special relativity we have if we have a particle with not infinite mass, with moving in the medium with speed higher than speed of light in the same medium?
Vladimir, what experiment was that where they found that electrons travel faster than c?
Oh, it is about 100 years already. Cherenkov radiation. You can talk. You can go to Wikipedia and see it. Guys, it's a well-known. Even gamma radiation, all this stuff, it's measured by Cherenkov measurement tool, instrument. You have particles moving inside of the medium with higher than speed of light, with velocity higher than speed of light. How come, guys? Simple like this. That's why we are talking about some vacuum. There is no vacuum. There is a cosmic medium. Many times I told you. Many times I mentioned already fast radio bursts. You have one source of your radio waves, no light speed and so on. And it's coming from billion light years ago from outside of us. They're coming to us, to our telescope at different time, different spikes, different frequencies, and higher frequency, shorter time, and time difference, it's a millisecond. You can calculate this time. You can measure it, even concentration of electrons in the cosmic medium. I know this experiment. I calculated these parameters before even this experiment and so on and so on. But we're talking about the speed of light, but we have fast radio. They're showing very simple, even for radio waves. We don't have constant speed of light or speed of radio waves. Forget it. Frequency coming to Earth at a different time. This is a value of special relativity, vacuum, all this constant speed of light. Constant speed of light, there is none. There is a gravity, the electrodynamic constant, and then you have your parameters of the medium. And in any medium, these electromagnetic waves will move slower. That's it, simple like this.
Through induction.
Maximum, it's not maximum of speed of light. It's constant, electrodynamic constant. Don't even talk about it because it's a constant.
Light moves through the medium through induction.
Well, if you have a refractive index which is less than unity, you get a faster speed than say in a vacuum. Now, I'm not sure if they use that explanation for the Cherenkov radiation, but certainly with regard to radio waves, which are bounced off the ionosphere, which allowed transatlantic communication, say at the beginning of the 20th century, well, that's normally explained by the ionosphere having a refractive index less than unity, and you're getting total internal reflection of the ray back to Earth.
Well, you're absolutely right, but we must talk about some ionosphere, whatever is around Earth, and then you can calculate all these numbers. There is no vacuum, guys.
The experiments or observations you mentioned where electrons exceed the velocity of light or radiation and such, that doesn't necessarily involve a relative motion. It's just that they just travel that fast if you're just stationary. Is that right?
Yes, you have a piece of glass, and you have in the same piece of glass, you have speed of light and speed of your electrons. And the electrons moving faster than speed of light.
So you're saying that relative to a light source that's slowed down by glass, electrons can exceed that.
Before glass, electrons moved less than speed of light. As I told you, maybe 80%. But inside of the glass, light moving 75%. And particles going with 80% of speed of light. And you can see so-named cones. It's a very well-known, it's a Nobel Prize in laureate in physics, that's why. And you don't know anything about Cherenkov location. Guys, take a look at it. It's a very important instrument right now for astronomy. Simple like this, guys. And this is a contradiction immediately. You have particle electron standard one moving with speed faster than speed of light in the same medium. And we don't have medium, guys. All our brain gymnastic. Ian, I love your definition today. Gymnastics, logic gymnastic, brain gymnastics. It's no value at all, guys. It's not a real line. It is only mathematics and our logic. What kind of science we can start even if we don't have a definition of principal points, of notions? What does it mean? Relativity. What does it mean, this one? What kind of science? You cannot start scientific in any definitions without notions. You have strong notions, and then start your theory.
It's very interesting that they can make electrons go faster than a light source within glass or a thick medium that slows down its propagation. However, though, if the light propagates through the air, or if there isn't a vacuum, say light propagates without a dense medium, I mean, they would have trouble accelerating electrons past that point. I would think. I would guess. They say that there's entangled particles, which is involved with quantum mechanics, which they experience the same state somehow because they're intertwined, and that communication between them occurs faster than the velocity of light. That's another possibility of something traveling faster than c. So.
One sec, guys, please take a look at this theory and you will see it's not only the experiment. There is a theory, there is a so-named cone radiation, and the angle of this cone depends on this difference in speeds and all this stuff. Guys, I'm talking about this effect, you never heard about it. Sorry. Please take a look and you will see how simple it is. And there's an explanation. By the way, guys,
it wouldn't apply without the dense medium, though. That was my point.
Okay, well, I've heard of this.
Because I don't want. Okay,
I've heard of this, Vladimir. So I know about it.
How do you measure the speed of
take
an
into
electron?
account your special relativity. How come particle moving faster than speed of light? How
The
come?
speed
I
of
don't
light
know.
in the medium. Speed of light
In the medium, but we live in medium. That's why all your speculations about vacuum, nonsense. Nonsense.
Well,
it's a waste of time.
There's
It's a good example, the value of the medium.
How do you measure the velocity of an electron in glass?
You have your electrons outside. You accelerated them, and then you push it into the glass. It's not inside of the glass. You have your accelerator, you have your electrons moving with speed 80% of the speed of light. They're shooting to the same glass, and you can see the difference between light and speed of these electrons. Simple like this. And it's a theory, guys, a very solid theory. By the way, I worked at this institute, academic institute in my life in Moscow, Lebedev Physical Institute. It was a laboratory by Cherenkov in our institute. That's why it is my history of physics, I started with in Moscow.
So you would say, for you, the whole special relativity speed of light is a constant is just nonsensical.
Yes, I told you many. I told you it's mathematics and logics. And I do like Jan's the definition. Logic exercise, or I don't know, massage.
Gymnastics.
Yes, guys, stop talking about it. There is no value for special relativity and general relativity at all, because basis of the theory is wrong. Harry, you talked today many times already about it.
Well,
Wasting our time. Let's talk about something else interesting, because for anything, if you have only one experiment contradicted to this theory, forget about it. That's it.
Yes, but we have this problem that you know, we're not allowed to say that it's wrong, even though we know that it's wrong. We're not allowed to say that it's wrong. So there's a kind of
Harry, what I've done in my life, I don't mention special relativity at all. Never speed of light, because there is no speed of light in vacuum, and so on and so on.
well,
Neglect it. Don't touch it, because you will never convince anybody who believes in it. It's a religion.
there have been many experiments which have allegedly proven that light has the specific value, the recognized value in a vacuum or through air. Air probably doesn't slow down light that much, I wouldn't think. However, though, I mean, it seems that light does have a velocity, whatever that it is, unless
All your
unless
experiments,
something else entirely.
all your experiments are
One sec,
two-way
guys.
measurements, not one-way measurements.
Well, that says
One
something.
sec, one sec, guys.
It would,
One
it would
sec.
seem.
There is no speed of light. In electromagnetic theory, there is electromagnetic waves with different wavelengths. Even visible light, or I don't know what you mean, it's our definition. We can see, Harry told infrared radiation. We cannot see it, but it exists. Means there is a speed of these wavelengths too.
Vladimir,
Infrared, X-rays, all of them.
Vladimir. Well, I mean, if you had a flashlight and you turned on the flashlight, the time. I mean, it doesn't take time for it to go from the flashlight to the wall, for instance. I mean, does it arrive instantaneously, or it
It
does
does
have
take
velocity
time.
somehow?
It does take time. If you take a look at some of the high speed film that's going on nowadays, like billions of frames a second, like a lot of frames a second. Well, maybe not billions, but millions of frames a second. You can see the light propagate from the source to the wall. You can see it moving from the source, hitting the wall, and then bouncing to the camera, and then moving along, and then hitting the end the end of the wall. You can see the propagation of light,
Yeah.
basically.
Well, I mean, that would seem to prove that light has a velocity, whatever that it is.
But I told
Well, that's
you
been
it is
established.
electrodynamic constant multiplied on parameters of the medium. That's it. And it's not light. Light, what we can see, guys, it's a waves, electromagnetic waves with different wavelengths. And don't talk about special visible light, what we're talking about right now, speed of light in vacuum. It's not speed of light event. There are electromagnetic waves of a very broad range, and all of them belong to electromagnetic theory by Maxwell. Please take electrodynamic constant, it's constant, and multiply on the parameters of your medium. And then you will find the real speed of light, but not visible light. Radio waves, electromagnetic waves.
I thought that Maxwell had suggested in his equations that the invariance of C, which is where at least